Hello, everyone. My name is Jaime Piña, and I'll be joined a little bit later by Wally Quevedo, and we're both from Sanadia Communications. Welcome to our talk, NATS All the Way Up. So let's start with the agenda first. So I'm going to start off with an introduction to NATS. Then I'm going to hand it over to Wally. He's going to talk to us about the NATS protocol and a couple of other cool things. And at the end, we'll both meet up for a Q&A. So let's start off with what is NATS? So NATS is a high performance messaging system that you can use to do a couple of different communication patterns within your app or organization. We like to focus on performance, simplicity, security, and availability. And we have a ton of client libraries. Here are some of the more popular ones like Go, .NET, Java, and Python, but we have a ton more, and we probably have one in your favorite programming language. So come and check them out. The NATS server itself is pretty cool because it's just a single static binary, which makes it super easy to download. You can just use curl and run it with /NATS server, and there you go. That's all you need to do to run it. We also have Docker images if you want to run it in a containerized environment. And our Docker images actually are also in a different architecture, so like ARM. So if you want to use it in different architecture environments, that's possible too. The protocol itself is text-based, and Wally will get into that a little bit later. It's pretty cool though, because you can use Telnet if you really need to do some debugging, and you don't need any other external tools. So it makes it really easy to debug. And overall, we like to keep NATS as low configuration as possible. So service discovery is actually built into NATS, which means clients actually only need the URL of one server, and then they can discover more about the topology. But Wally, again, will cover that a little bit more in detail later. But overall, we like to keep the APIs for NATS pretty simple and straightforward. Something else we'd like to mention is that this year, NATS is 10 years old. So NATS has been around for 10 years, and it's been 10 years of high performance messaging, but it's actually also been 10 years of pretty good stability. So over those 10 years, NATS has obviously evolved, and there's been conscious effort to try to make changes in a backwards compatible way so we don't end up breaking people's code. A story I like to think about is we had a user a few months ago that was using NATS 1.0, and they wanted to try out some features in 2.0. So the upgrade path for them was actually super easy. All they did was replace binary, and it was a drop-in replacement, and they got automatic performance boosts and a couple of new security features. That's pretty cool. Doesn't happen with a lot of projects, and it's great that we're not breaking people's code. So here's to 10 more years of NATS. So, all right, now what about messaging? So in NATS, we put messages on subjects, and they can be simple. They're just strings. They can be simple like weather, or you can create hierarchies by using the period or the dot character. So in the example here, we have weather.us.co.denver. And so that's some subjects that are built with hierarchy. Now, we can select different parts of the hierarchy using wildcards. So we can select parts dynamically with wildcards. And we have two types of wildcards. The first wildcard matches a single subject token. And so, for example, in this first example, we have foo.star, and this will match foo dot, and then one token at the end, anything at the end. And so, for example, bar or baz. We can also move the token to the middle, though. So like in the second example, we have foo star bar, and so that'll match anything in the middle there. But it's only one subject token that gets matched. You also may want to match basically everything from that starting point. So for example, foo.greater than will actually match everything from foo all the way down. It can be one token, or it can be 5 tokens that'll match everything all the way down. And so a place where this is actually kind of handy is if you're trying to debug something or trying to introspect kind of what's happening in your NATS server, you can subscribe to greater than at the root level. And this will subscribe you to all of the messages that are going through NATS flying around, and you can see everything that's going through there. In addition, though, we also lock this down with permissions. So it's not like anyone can just access all of the messages in your entire NATS server. You can configure users to be able to listen or publish to certain topics, and you can use wildcards there as well. So it is secured, so not, it's not free reign for everyone to just listen to it for whatever they want. So messages go on subjects, but then how do you like send the messages, right? And so in NATS, we have two main ways to kind of do that, two main styles. There's streams and services. So a stream is a continuous flow of data. You can think of it like when you send your live location on WhatsApp, for example, you're publishing a stream of location data there. And on the receiving end, your friend is subscribing to that location stream so that they can update the UI on their app. On the other hand, we have services. So in NATS, anything that's a request and response style interaction is called a service. So a lot of us are probably already familiar with this concept. This is like RPC or HTTP. It's just when you send a request, you wait for a response. So let's look a little bit more in detail for streams. So for example, in this diagram, we have an example of streams. And on the left-hand side, we see a NATS client that's publishing data on the subject foo. On the right-hand side, we have 3 clients that are listening to foo, and they each get a copy of foo. And they can react to that however they want. The code for that is pretty straightforward. There's not a lot to it. You connect to the server, and then you either subscribe or publish. There's like no boilerplate at all. And both of these calls happen asynchronously. So that handler will fire asynchronously when it receives a message. On the other hand, we have services. And again, we're probably used to this more. Just like HTTP, you can send a request and you wait and you get a response. So this creates a one-to-one relationship. And the code for this is pretty similar. So again, we start by connecting to the NATS server, and then we can subscribe, or in this case, request instead of publish. So if we look at that request line, we see NC request help. Help is the subject that we're sending a request on, and need help is the payload for our request. And we also have a timeout there of 1 second. So the subscriber that's handling this message that you can see above that has up to 1 second to respond to us before we time out. And in the handler, you can see m.respond is responding back to the request. And so it's important to note that this request call is blocking, unlike publish. So we'll wait here up to 1 second, and then we'll move on. Hopefully we get a response, but if not, we get a timeout error. Yet another way to do messaging in NATS is with queue subscriptions. So NATS actually has built-in load balancing baked right in. And so this means you don't need another component just to do load balancing. This is pretty cool. So on the left-hand side, you can see there's a NATS client publishing data on foo. And on the right-hand side, similar to the streams example, if you remember a few slides back, but the difference here is that not everyone on the right-hand is getting a copy of the foo message. So in this case, it's only going to the first client. And because this is being load balanced, NATS will randomly pick one of the people in your queue subscription to get the message. So it'll get one at a time. And this is a great way to horizontally scale an application, for example. So we talked about subjects and how to send messages on subjects. Now we can talk about accounts, and accounts allow for multi-tenancy. And multi-tenancy is great when you want to isolate different teams or different organizations or different groups in a company. So for example, on the left, you're looking at some NATS configuration language. And so this is the language that you can use to configure the server, not just accounts, but other things as well. In this case, we're looking at accounts, and we have 2 accounts here. We have an Acme account and a CNCF account. And then we have different users, Alice and Bob. And in this case, we decided to use password authentication, but NATS actually supports a wide range of different authentication schemes. So depending on what your company needs, we probably support it. And an interesting thing we're doing here is we're exporting, in this case, a stream, so that other people from other teams can consume that. So in the Acme account, we're exporting on the right-hand side, you can see we're publishing on acme.hello, and that's being exported as defined by the configuration on the left. And the cool thing is that in the CF group, they can import that. And in this case, we've actually aliased, or sorry, not aliased, but prefixed the import with imports. So the CNCF guys could use imports.acme hello. And so this really gives you the ability to separate, concerns among groups in your company and creates nice isolation. Of course, permissions also work with this model. So, depending on what subjects you have, you may want some teams to be able to publish to some subjects and not others. You can totally do that with NATS. And here's basically the same thing with services. So it works both with streams and services. And on the right-hand side, you can see some service example code. Okay, so now the NATS protocol, and here's where I'm going to hand it off to Wally. He's going to talk to us a little bit about the NATS protocol, and he's going to mention some other cool stuff about NATS. And I'll join you guys at the end for a Q&A. Thanks.
Thank you, Jaime. So in this section of the talk, I'll be talking about a brief history of the NATS protocol and its implementation in Go. Give you a quick overview of the engine from the server and some of the techniques that it's doing in the client. So the NATS protocol got a really good start. It has original implementation was in Ruby, written in 2010, October 2010. So it's actually a decade-old project already. First pass was about 15 lines of Ruby. And what is surprising is that in 2020, this same version of the protocol is still compatible. Of course, it was being in Ruby, it was using regular expressions, and then it was very succinct, but the performance was not great. But the design itself from the protocol was still in use today. So how it started and how it's going. It started with the same number of commands, pops up to publish and subscribe, send messages, unsubscribe, to stop receiving messages, connect to both for establishing an authenticated connection to the server, and info, which announce you some metadata, some of the state from the server, is the first line that you get, and message, which is are the awaited payloads that you receive from the server. And there are some other miscellaneous protocols, like for errors and hacking, as well as a ping pong interval for keep alive. This was the original implementation of the protocol, and in these 10 years, there has been only 2 new protocol commands, and they haven't even been released yet. I mean, they're in the code, but this is for an extension to be able to have published messages that can have headers into both the published and received messages. So it is it's very stable, the protocols, what I try to say. And this it's called the most used protocol are the pops up and messages commands. So, and what is really cool about the NATS protocol is that you can just use a simple telnet connection and start typing out the protocol and have a very basic producer and consumer interactions. In this case, you are publishing on foo 5 bytes, and then on foo, you're sending another, you're making an interest on a subscription named foo. And then when the producer sends those 5 bytes, the server will dispatch you a message on the foo subject, expecting you to read those 5 lines, those 5 bytes. And because a pure publish subscribe system, both the publish and subscribe and message commands are the core building blocks to be able to have RPC interactions as well. So you have, in this case, a requester is just a unique subscription. So we have a unique subscription on a subject, and then when we expect to have something like a service, for example, in this case, subscribe on echo, and in this case, the V1 is going to create a queue group to be able to have the load balancing happen between those workers. So now when the requester makes a publish on echo, tagging along an inbox, it is going to be able to await a response on this unique subject that then the other service is going to be publishing into, and then the client is going to be, the requester is going to be able to process that response. So it's how RPC is working using the same NATS protocol. For this unique inbox generation, we needed for it to be very high performance. For this, we're doing using a project called NUIT. So you can find it on the NATS.org as NATS.io NUIT. It is it uses 12 bytes of crypto data, so it gets some bytes from the random, and then the next segment of the UID is going to have a pseudo-random incremental jumps. So you can see once you are creating many inboxes, you can see that only the last few bytes from the inbox are going to be changing, and it is until it has to run over of that last part of the segment that is going to make an increment for the inbox from A to B. So this is where the inbox it is changing, and it's going to be switching between this all those alphanumerical sequence, and it's very, very fast. Can send can generate around 16 million identifiers per second. So this is what we're doing for request response to not induce any latency. And the NATS protocol got rewritten from Ruby into Go in 2012. That's one of the reasons we're at this conference. And Derek Collison, who created the NATS project, has talked previously at GopherCon about some of the techniques that he implemented to make the server very, very fast. But yeah, compared to in a nutshell, compared with the NATS implementation of the server, the client, the NATS server, the Go NATS server can send millions of messages per second. On my laptop, I can get, for example, something around 4 million messages per second with a small payloads. And a machine like the one from Derek can send around 70 million messages per second. So it will be really cool how it runs in one of the newer M1 machines, for example. At its core, the NATS server engine consists of both a reading loop and writing loop for each one of the clients. So whenever you establish a connection against the NATS server, it is going to be always established connection where has a very the reader loop is going to be processing the bytes from that are being sent by the client, and then it's going to be have another Go routine that is responsible of having the optimized flushing of the bytes for that client. So all established connections are at least 2 Go routines for clients. The reader essentially is a very optimized parser that it is not like the regex-based implementation that I showed from Ruby. It is a 0 allocation parser around nowadays like around 1,000 lines of code. So it goes state from state from the parser, and then gathering all those bytes and being very careful about the allocations and how it is gathering those bytes from the client. And you can have partial reads as well. And then from the other side, from the writer, there's the flusher that is responsible of sending the outbound data. And it is has some fixed sizes on the signaling that, in this case, whenever it collects at most 10 flushes pending to be signaled to the server, is going to be forcing a flush. But it can also happen whenever the buffer gets up to like 65 kilobytes. And this part of the code is very important because it gives NATS one of the best traits, that is it protects itself. In this case, when the NATS server cannot make a write to one of the clients for up to 2 seconds, what is called the write deadline, then that client is not very healthy, so it's going to become a slow consumer. And the slow consumer is what the NAT server does to be able to protect the whole system from causing the server from accumulating too much memory or causing latencies, increases into the latencies from other clients. So in this case, it will wait for a single client to up to 2 seconds to read from the pending data that it has, or it is going to accumulate some of that data up to 64 megabytes by default and buffer that for the client. If any of those limits hit, then that server is going to be disconnecting it. And another interesting part of the code is the sublist try structure, routing structure, that it is useful to match the different interests depending on the wildcards, on the greater than, which is a special type of wildcard that also matches everything under that tree. On version like NATS v1 implementations, you could get some issues once you had like hundreds of thousands of subscriptions. But with some of the optimizations that went into the NATS v2, and for this part you can look at some of the sublists and the client in the repo from NATS repo. Now it supports millions of subscriptions. So there was a lot of optimizations for the fan out of the clients. But what is really cool also from NATS v2 and the enhancements is that now it has very support for flexible network topologies. So the NATS at the very beginning was a single server that it was really good for microservices because anyone within the same data center, they could be all connected to the same NATS server. But it has evolved nowadays where you can have very complex topologies. In this case, I'm showing you something what is called the NATS adaptive edge architecture, where you have not only a single NAT server, but a collection of clusters of NAT servers, which are also clustered with other regions of NAT servers running on other regions, and some special type of connections called for IoT, optimized for IoT traffic that we call the leafnode connections, so edge connections. So those topologies are now, you have like started with a single server, then this server became like a cluster of NAT servers, and now you can make a cluster of them, and we call those the super clusters. And you can have leafnode connections to any of those types of servers. Instead of the code, we call them the client connections, which are the classic style of NATS connections, where, for example, when I telnet to the demo.nats.io on the 4222, those are called client connections. And as we do, not only can you have NATS connections, but also have WebSockets and also incoming MQTT support. And we connecting within the same DC, you can have route connections. Those are for providing the fast failover. And also when you want to connect from one cluster to another one, you talk about gateway connections. And so the edge connections are those leaf connections. So the NATS clustering within the same data center, it is usually it's a full mesh type of topology. Usually it is 3 to 5 nodes. Although within NATS v2 enhancements, you can have very large clusters as well. But usually just 3 to 5 nodes is recommended. So the clients are responsible for handling the reconnection automatically. And what is also very cool is that using the info protocol, you can have the discovery of the client's network topology as they are joining and going. So client connected to the same cluster only needs to be aware of at least one of the other servers to be able to message and interact with any other of the other clients that are connected in the cluster. Compared to NATS v1, NATS v2, the NATS v2 NATS protocol became multi-tenant aware. So now everything exists within an account. And what used to be like the global account from NATS v2, and this is some of the NATS protocol from the v1 series, now is part of a global account. And in this case, it becomes the $G default account, but you can have as different accounts or subject namespaces as it fits your organization. And all of those building blocks are also can be put to use in a multi-region setup using the gateway connections. So in case you have the same accounts and the same subject namespaces within the different regions, you can use those gateway connections and connect those clusters. In the way that this the topology works is that each one of the servers needs to have at least one connection to one of the servers from the other cluster. So in this case, let's say that this is well, this cluster A, we need to have at least two connections, one for the from the cluster B and cluster C at the bottom. And then if you, in this case, I have two clusters, one's in Singapore, the only one in Amsterdam. I just need to connect to the cluster. I need to connect to any of the nodes that from the Singapore cluster to be able to forward a message all the way to the cluster in Amsterdam. And then we have the leafnode connections, which are very cool because you can create hub and spoke topologies. So by having this other supercluster in the middle, the leafnode connections can create cluster themselves. So in this case, the leafnode A and leafnode B, even though they are like remote to each other, they can, by using the same cluster name, they can, using this other supercluster as a bridge to be able to interact with each other, which is one of the things you can get with the adaptive edge architecture that I mentioned earlier. In terms of the code, it is all using the same optimized parser implementation, and the traffic adapts depending of which is the connection type. In this case, the message is going to be routed for a cluster in this case, or it could be a leaf node message. So that's how the routing and message flows depending on the interest in the protocol. And one example of this in practice is one very cool project that we saw recently is the from IBM, the SpaceTech CubeSat project, where it was making a simulations of using the NATS adaptive architecture and the leaf nodes and the gateways to create dynamic clustering of satellites. So in this case, we have a single ground cluster where, and through the ground cluster, the leaf nodes A and B were able to communicate to each other. And as they were getting close, for example, we could say that they themselves, instead of using those leaf node connections, could create a cluster themselves and stop using that other connection to communicate with each other. Also try to use show some of the WebSockets connections support that we have. We have a simple application called nats.chat, where you can send a request to get access to the server, to the service. And we're using some of the streams as they are represented in the chat application. So for example, you can have a general, all of the rooms are a stream of messages. And also you can receive DMs as well. So I'm going to show you a little bit of creating an example. GopherCon, and it's GopherCon. So now I have created a new user, this is an established WebSocket connection. Have been generated a pair of credentials for the Gopher 7 user. I have been issued user JWT. And this will allow me to be able to interact with other users, all using the same WebSockets connection. So I will send another message to Jaime. And also can publish a message to general. And we'll have this demo site as well running during the Go Systems Conf conference. And so that's it for the talk, and looking forward for the joining for the Q&A. Thank you.